in the closed path. And when I say in the closed path, of course, I mean all those vertices like this one, this one, this one, this one, all those. These are the ambiguous numbers. Half of them are alphas, and the other half of them are alpha conjugates. If you apply this G, and since X, Y are elements of the modular group, we have this condition satisfied by them. Otherwise, they will fall outside the modular group. In that case, if you consider this alpha as a vertex here, and you apply xy square, etc., come back to alpha, you get a quadratic equation. And that quadratic equation, like this one, has alpha as a root. This is the trace of the matrix related to this G. Thus, M, which in this case we have denoted as k square minus 4, where k is this is k. So M is the entire, this discriminant. Thus, I hope you understand what I'm saying. M is k square minus 4, so k is a plus d, which is the trace of a matrix representing G. Since this G is a word in xy, an element of G, therefore the trace of mg representing G can be calculated as follows. And then there is a method to calculate any trace depending upon G, of course. The trace will be then this one, 2 plus this thing. And if you now take, now here again, I paused for a while. When I looked at a particular case and I said, okay, I will take all these n1, n2, n2k equal to 1, what happens then? In that case, a very important particular case emerged. And we got this, alphas, the two solutions of the quadratic equation as Fibonacci golden numbers. And the equation we got was this one. And that's how we started getting the kth Fibonacci numbers. And that was a very promising thing for me to look at. Many years later, when I had done some work in other field related to, of course, this whole setup, I gave this problem to one of my students, Umar Hayat, if you remember, asked him to generalize this, and then he obviously worked on this aspect of that. I'm giving you an example that how my students were working in this area. They were basically offshoots of some cases that I kept on leaving without having them generalize myself. So here there was a situation, for instance, where I came across the sequence of Fibonacci numbers out of the action of the modular group on real quadratic irrational numbers. And then I kept it there because my attention was somewhere else and I wanted to do something else. I continued sequentially producing the results in the same area, but then I left this behind. When I got the opportunity to look back at this particular situation, I gave it to one of my MPhil students, and he came out with a very good result, which eventually lead to many other results, and they are now embodied in two very good research papers published in, I won't use that word, in journals which are considered good previously and now also. Okay. Then once we have done that, we realize that actually if we take action beyond real quadratic irrational fields, what do we get really? Can we just continue like that? But then there was a logical end to that. We realized that the sort of work we are doing, actually, if we continue and start considering other similar algebraic spaces, we may not get anything fantastically new. So where do we go next without breaking the sequence of results that we have been producing? The next thing was to look at the algebraic numbers. These are the numbers contained in cyclic cubic extensions of the rationals. So we are again dealing with rationals, but now in a different category. The category is of the cubic cyclic extensions. This all discussion justifies what I'm saying here, that we need then to look at the action of the modular group on these kind of fields, because we started with real numbers, rationals, real quadratic irrational numbers, etc. So now we need to confine ourselves to the action of the modular group on the cubic cyclic extensions of the rationals. This provides the logic, and once we have looked at them logically vis-a-vis the transformations, the linear fraction transformations, we see that eventually we get these kind of equations. And we can say then, thus every cyclic cubic field can be generated by adjoining a root of the above equation k is the root for some rational k. Conversely, for rational k, either the equation has 3 rational roots or its roots generate a cyclic cubic extension. So we are getting into deeper water, and that makes things difficult actually for us to deal with. But we managed to come out with results. They were quite good results. Then after having done that, we also realized that if we look at the sort of fragments we are getting in these actions as a result of these actions in the coset diagrams, and remember that there is a ring homomorphism between these fields, which are infinite fields, to the fields which are Galois fields, with the infinity as a point. In that case, our entire system that we have done or developed so far, that gets converted into diagrams in the finite cases. That is, in the case of diagrams that emerge from the action of the modular group on projective lines over Galois fields, FQ, where Q is a prime power. In that case, we use X and Y and use also the modular arithmetic, because we are now dealing with the elements from the finite fields, including infinity. In that case, we get a finite coset diagram, which is the homomorphic image of the infinite coset diagram that we have seen so far, whether in the case of rationals or irrationals. Their homomorphic images are now these sort of diagrams. Look at this third patch here. This is a closed path that occurs in the infinite coset diagram. But when we take its homomorphic image, it becomes this. And this homomorphic image exists in this kind of diagram. So then we need to know, remember, we had a typical type of closed paths in the infinite coset diagrams, depicting the action of the modular group on real line, rational projective line, and and irrational projective lines. So in all these three cases, whatever we were getting in form of coset diagrams and the fragments, they get transformed into small fragments lying within these coset diagrams. Sometimes very difficult to even see where they are lying. That themselves create problem for us. But we have developed methodology by which we can actually find out that they are homomorphic images of some fragments or closed paths that we started with initially in the case of infinite diagrams. When I say infinite diagrams, it means real, rational or irrational projective lines. The next question comes, when certain type of closed paths exist in these finite coset diagrams, they just don't occur whenever they feel like. They occur under certain logic, and we wanted to know that because it is important for us to know. And it happens so that we can then find out through certain system that this kind of fragment occurs when it satisfies certain conditions. Similarly, when the fixed points of x exist, when this cap exists, when the fixed points of y exist, when the fixed point of t exists, and so on and so forth. When we come to the stage where we have to see action of the modular group through the coset diagrams,